So we're going to talk today about. We'll look back at the end. Let's see. I don't know. I didn't look at last period, so we'll see what it is when we get to the end. We're going to start talking about linear speed, arc length, time, all this stuff. So the first part. Linear speed, arc length divided by time. What's arc length? Okay.
Whoa. You have to do it on everyone.
Every time I restart my computer, I do it, I guess.
Okay, let's try this again. So arc length we have as what? What's the formula we use for arc length? Yeah, so S equals R times theta. But that wasn't just plug it in. We had to be careful about something. Theta has to be in radians. So make sure that you remember that if you use this formula to get arc length, you must use radians to work with it. So that makes, when I find this angle, this arc length of this linear speed, which is the same thing as like velocity of a car, speed of a car, that's all the same stuff. Right? So it's going to be R theta divided by time. It's the same formula that we've used before, but just think about it. If I told you that I'm going to rotate 90 degrees in 2 seconds, then what's my angular speed? How fast am I turning? 45 degrees per second. So that would be what we call angular speed here, right? Linear speed would be how far was it, first of all, how big is the circle that I'm turning with, right? And how far around the outside edge did you travel? If you traveled 20 feet in those 2 seconds, then how fast would you be traveling in feet per second? 10 feet per second. Okay? So linear speed turns out to be things like you're used to with miles per hour and feet per second. Angular speed would be like radians per second or degrees per second, or the time frame can be anything, seconds, minutes, hours, milliseconds, whatever happens to be going on at the time. But what we're going to work with today are this formula and this formula. But doesn't that seem really almost the same formula? What's the difference?
The R is on.
This has got R in it, this doesn't. So if I travel degrees, if I have degrees and I rotate through a certain amount of time, then I just simply take the number of degrees or radians I traveled through, divide it by the time. That's really straightforward. If I have a radius of a circle, the longer the radius is, okay, the further the traveling, the further the distance I would travel. Okay, so that's kind of where we're going with this. Okay, so let's talk about, let's see. Wouldn't that be nice, right? It's the calibration's off. There we go. All right, so here we have a clock. The second hand of a clock is 10.2 centimeters long. I want you to find the linear speed at the tip of the second hand. In other words, how fast is it traveling? What units are we going to end up with? It's a velocity, it's not a distance. It would be what?
Centimeters per second.
Good. It's centimeters, right? So it's centimeters per second. When you have, in this case, centimeters, how did you know it was seconds? It's a second hand. So let's just write out what we have. We have linear velocity we're going to represent with a V. Okay? That would be R times theta divided. Okay? You look in here, you have this. What's theta? And what's time? Time is 1. Okay, interesting. Haven't had that. Well, let's just pause for a minute. 1 would be a bad one to choose. Okay? Do you know? Well, we'll see in a minute. Okay? So I had someone say they felt that 60 was a good choice. That was okay. What's another good choice for time? 30 would be okay. 45, 15. Those are all probably what I would expect people to choose. You could choose others, but let's move on. Let's go ahead and pick the appropriate theta that would match with these time frames. What about 60? Nope. What's the rule for theta? What does theta have to be in? So what would 60 be? 2 pi. How far does the second hand travel after 60 seconds? All the way around. 2 pi. What about 30? Look at the clock. How far is 30 seconds on the circle? It's half, so pi. What about 45? No, that would be 1/4. That would 1/4 would be 15, right? So, pi over 2 would be 15, and 3 pi over 2 would go with 45. Shh, listen. You see the clock? Look at 15 seconds. The angle that you travel, if you have a clock, the angle that you go through for 15 seconds is what? 90 degrees. If you go all the way to 30 seconds, what angle did you travel through? 180. And if we go all the way around, that would be 270 degrees, or 3 pi over 2. Now I expected the most common answer to be all the way around. That would be 2 pi because it's 60 seconds. That's how many seconds are in 1 minute. Okay? So you use whichever one you want. I'm going to use 2 pi on the board. But you're going to work it out right now. You can use any of them. Take a second and work it out. So the answer would look like this. We're going to plug all this stuff in. 10.2 times 2 pi divided by, we're going to use 60 here. These two would, you've got your angle, which is 2 pi and 60, or I used pi and 30, or whatever. They would adjust because it's traveling the same speed the whole time. So you pick however you want to. That's going to turn out to be 1.07 centimeters per second, which makes sense. If you look at that, that clock is probably close to about the same size as the one that we're describing. So every second it travels about a centimeter. Okay, that's a little bit bigger than the one in the picture. Questions about this? This is very traditional. You should be able to do this one no problem. The tricky part about this question is it doesn't give you all the numbers. It expects you to be intelligent and to think about what is it saying, what is it giving you. You know time, you know seconds, and it's on a clock, so that should be kind of intuitive. Be able to do that. You will be asked to reproduce things like this. Okay? Oh, by the way, I'm going to be attempting to get some apps on the iPads that you can take notes on, literally right on the iPad. I'm going to get some styluses, or however you say that. Okay? And you'll be able to use them in class. This app is one I've used. I wrote this through this in an app called Notability. Hopefully we can get that one. That one's a paid app. What? Oh yeah. You like my ruler? It gets better. So make sure that you, if you have an app, if you're used to writing in notes, let me know. If it's free, we could probably get it put on there. If not, you can write it up on the one I wrote. Whichever one we get to, you can email yourself the notes. This way you can import pictures and text. This one records audio at the same time, so you can email yourself the picture as well as the lesson from class. So anyway, we're looking at getting into that. Anyway, 10 inches radius lawn roller makes 1.2 revolutions per second as shown below. So find the angular speed of the roller in radians per second. So what is that? That happens every time. What is 1.2 revolutions? That's angular speed. They gave me the angular speed. They just gave it to me in a different unit. What's a revolution? It is one complete circle. It's 360 or 2 pi, whichever one you want to think about it. I want you to convert, for the first part, for A, convert the angular speed from revolutions per second into radians per second. Go. So let's look at it. You've got 1.2 revolutions per second. And I suggest that you do it this way. Treat it like fractions. The per is your kind of your division symbol. And so we want to convert this. And I'm going to have to cancel out stuff. It's already in seconds, so I don't have to worry about the seconds. I do have to convert revolutions into radians. What's my unit? What's my conversion factor? Well, revolutions on top. So I'm going to have to put that on the bottom for it to cancel. But what is a radian measure that's equal to a revolution?
2 pi.
Yeah. 2 pi. It's one full circle. Could I have done half a revolution? 0.5? And that would have been equal to how many radians? Half. So if I have half here, half that, so it gives you 1 pi over 0.5 revolutions. You could have done anything you wanted to. This makes the most sense. Okay? On a side note, if you have pi as a degree measure, you don't have to put RAD for radians. If it's a whole number, put RAD just to make sure it's radians. Okay, so this cancels. You have 1.2 times 2 pi, and that would be 2.4 pi, or what's the decimal?
7.540.
Okay, and what would my units be in this case? Hopefully it's radians per second, right? That's it. The next part asks me how fast is the tractor pulling? How fast is it going? What's wrong? Okay? That's linear speed. Tractor drives in a straight line, correct? Or, well, it drives in a linear fashion. So we have to figure out linear speed. So for part B, what formula are we going to be using? Okay, just so you know, omega, lowercase omega, looks like a W, just a little curvier. Okay, that stands for arc. Okay, this is angular speed. That's the omega. The V stands for linear speed. Velocity is kind of where that comes from. Now, if we're going to do this, how do we do this? What do we have to do? So, I've already got angular speed. Do you notice what is this right here? What's that part? That's angular speed, right? Okay. I totally wrote the wrong answer there. Why y'all correct me on that? You don't want to embarrass them. D. We're looking for linear speed. So you've got angular speed already. So I've already got this. This answer is right here. That's what you found in the part A.
So what is the W you go with?
This is W. Angular speed. I was thinking that, but didn't write in the right place. Okay, so you got this. So we take 7.54. We're going to multiply that times the radius, which is 10 inches. So you're going to get 75.4. That's inches per second. It didn't ask me to tell me how fast it was going. I could convert that to feet per second or miles per hour if I wanted to. Okay, but it shouldn't be going that fast. It's traveling 75 inches is how many feet? A little more than 6 feet. Okay, so for a tractor that's moving quite fast. Questions? Angular velocity, angular speed, linear speed. I'm going to put another problem up. You're going to work this one out yourself. Okay? So let's see. You gotta love these things. Oh, that's right. It should be able to do it on its own, depending on what you feel.
Can you just click the pic?
I can't. Like my car. Okay. This is really frustrating.
Why don't you roll on your computer?
Because my computer's all over my desk. Alright. Shh. Here we go. Go for it. Okay. Shh. Listen carefully. This is one of those things where I expect you to be able. This is not a difficult problem. Okay? In terms of levels of 1 to 10, this is probably 10 being the hardest. This is like a 4. Okay? No, absolutely not. When you plug this in and you write down what they've given you, it's like plugging it into the formula. Here's the formula. Here's my information. Let me plug it in and work it out. There's nothing else to this. Shh. Don't talk. I want you to listen. For the first time all year, I want you to listen. Some of you. Listen carefully. You have to think about what you're given. You can't, if it's not written for you in a form where it's just like, here's the answer, get used to that. That's not going to happen. Okay? The word problem says, can you take the information, can you read through the problem, and can you apply, okay, this particular problem in the book, there is no picture drawn. I drew the picture because you need a picture. Okay? Your picture needs to be, it doesn't have to be like this. Okay? Right, but let's put some information on my picture, right? So here's the center. What we know is that distance, it told us that 6,400. Right? So the radius of the Earth is 6,400 kilometers. But my satellite's not on the ground, is it?
No.
How far off the ground is it? So go out here. That is another 1,250 kilometers. So what is the total radius of my problem? It's 7,650 kilometers. Shh, listen. My picture made that super obvious. The satellite doesn't orbit on the ground, but the satellite orbits around the Earth at a certain distance away from the Earth. Hence, that's why they gave you 2 different values. They wanted to see if you could put 2 and 2 together, okay, to see if you could figure out the total radius, because that's a big deal in this case. All right? Next part. So let's just go ahead. Our formula for this problem is linear speed, linear velocity, and so it's going to be r times theta divided by time. Make sense so far? And so once we get through this problem, we have to figure out, well, we got r, boom, easy. What's theta? And what's time?
2 pi. It's 2.356. It's a full rotation. That's 2 pi.
It makes a full rotation at 2 pi. Why would I automatically choose 2 pi?
Because that's 360. But it's easier if you choose
No, they told me exactly this. How fast is it, how long time does it take to go all the way around? Now, could I have chosen another value? Yes. If I had chosen 45 minutes, that would have been half a revolution. So that would have been just pi. If I chosen, I could have chosen 3/4 of that, but if you chose 45 minutes, so then your theta rate would have been pi. Okay?
I thought 45 minutes was 3 pi per test.
45 minutes of a clock, yes. But my revolution, it takes this satellite travels in this direction. It takes, so let's say it starts here, right? When it gets exactly on the opposite side of the Earth, it's halfway through its revolution, correct?
Yeah.
So that would have been after 30 minutes, or no, after 45 minutes, you would have seen that. Is that working? Great. There is a way. It was working this morning. I don't know what setting it's going to be on. Right? So after half a revolution, 45 minutes has passed. So it's directly across. What's the angle it traveled through? 180. We're not on a clock anymore because the total now is 90. Previously, the total was only 60. So that's the difference what you're thinking. So now I just plug it all in. So we have the radius of 7,650 times my theta, that would be 2 pi, divided by my time, 90. What do you get?
Always it's easier. It's 534.
Is that what it is? I couldn't remember. So it's 534.07 kilometers per hour. Or minute. It's minutes. That's pretty fast. Okay? 534 kilometers, not per minute, or not per hour, but per minute. So, but it's got to go a long distance. So you would expect that to be traveling in a relatively fast time. Questions? If you left your answer in terms of pi, or if you have it in the decimal format, it's okay. Okay? Now, let's go on to the next one. Probably won't finish this one. Your homework's on the board, by the way. Okay, I've got 5 minutes. We'll at least start talking about it. Okay? A car is moving at a rate of 40 miles per hour. Try to stop. Okay? She's going to skip. 40 miles per hour, and the diameter of its wheels is 2.5 feet. Find the rotational speed of the wheels in revolutions per minute. How fast are those tires spinning? Take a minute and think about that. Let's just let's talk about the problems, because I'm not going to finish the whole thing here. Let's talk about the problems you see to start with. Okay, number 1. Miles. Shh, please be quiet. You have miles per hour. That's how fast the car is traveling, but my radius is in feet. So what's the problem? Or my diameter is in feet. I've got feet and I've got miles. I need to convert them to 1. So 40 miles per hour. I want to convert that into at least feet per hour. Okay? So listen carefully. We'll convert this to feet. 5,280. divided by 1 mile. And so when I convert that, the miles cancel. Okay? We need to go to, look at what we're trying to get into. I have to go to revolutions per minute. So let's go ahead and convert this to minutes. So here we have to get rid of hours, so 1 hour here. That's the same thing as 60 minutes. So when you multiply 40 times 5,280 divided by 60, you get 3,520 feet per minute. So the only thing I did was I converted the velocity, 40 miles per hour, and how many feet per minute is he traveling? Haven't done the problem yet. Find the rotational speed. Okay? So the last person is find the angular speed of the wheels in radius per minute. Sometimes it's actually a little bit easier to kind of find B first and then go back and find A. Angular speed, that's linear speed, right? So linear speed is V equals radius times theta divided by time. Well, I want this part. So if we divide both sides by r, V over r equals theta over time. That's angular velocity. So take your 3,520. We divide that by 1.25. Where did 1.25 come from? Remember? That's the diameter. So you're going to have to take that, cut it in half to get the radius. So my radius, in this case, is 1.25. If you divide that value, I don't have an answer, would say 3,520 divided by 1.25. That would give us our angular speed. Homework is here, by the way. That gives us part B. If it's traveling that fast,